Fantastic. Right. So we welcome Mario Berta from Aachen University. He was previously at Imperial and AWS also. And yeah, I mean, he's an expert in quantum information theory in general, and lately also on algorithms and error correction, I guess. And yeah, as I was saying before, he's one of the authors of this wonderful paper on multivariate trace inequalities, where they explore generalization of codon function inequality to multiple matrices. And this was really a breakthrough a few years ago. But today he's going to talk about quantum state preparation without coherent arithmetic.
Thanks a lot. Thanks, everyone. Yeah, awesome. Good. Yeah. I used to work on information theory mostly, but yeah, the last 2 years I spent at AWS and some results on algorithms, and in particular, this one is kind of a cute, simple little thing that I think deserves some attention. So I'm trying to present it from time to time. Anyway, I think the main slides are quite superficial. If you want to hear more, let me know. Also, please interrupt anytime. Yeah.
You can also just press on the screen to
really.
Not really.
But like that, and we see it over here. No, it's all good. But can you see it like that, Jens? Or you see it on your screen?
I see it on my screen.
Okay. Yes. I just don't want to, step over this. Good. Yeah. So the problem is very simple. You just want to encode the values of a function in the amplitudes of a state. So here in this setting, right, we would pick some interval AB, and then you use some discretization, some grid. So you might use some uniform grid, and then you choose a number of points where you want to evaluate your function, right? So the total number of points here will be 2 to the n, so exponentially many in n. And then you want to have these amplitudes of any function, right? In there, we look at real functions. You can also look at complex functions. And of course, if it's a quantum state, you have to normalize it. And yeah, many people looked at this problem. I think one of the reasons it's particularly interesting is also because if you want to prepare a state like that from data, the data has no structure. You need these kind of QRAM architectures, which are very expensive. However, if you can kind of compute your data, if it has some structures, you can compute it for a function. From a function, then you can do it like in this coherent fashion directly, and things become much cheaper. So this is kind of like a fully quantum task, if you want. And yeah, we just kind of want to optimize the resources that are needed to do this. Okay, and it's also part of many algorithms. So if you can optimize the resources for achieving this task, I think it's broadly useful. And the other nice thing about this, you don't really have to compete with a classical algorithm, right? Because otherwise, when you do a quantum algorithm, there's always going to be a classical algorithm that is nearly as good. Here is just a quantum problem that has multiple applications. So let's optimize the task. Yes.
Question: why do you restrict your function to real numbers?
No reason, it's just similar, but there's not. Yeah, so this I already said. It's an important subroutine.
And uniform is taken for simplicity, right? Because
everything
sure
taken for simplicity.
It's uniform, but never mind.
Exactly. Actually, maybe I should have just used -1, and then right.
You're reminded of a talk by Frank Westrate where he had like a 1 hour slot and made it to the first slide.
No, this is simple. It's all simple. So it's going to be fine, I think, hopefully. Yeah, so we want to minimize, the number of gates we need, or maybe the depth of your circuit. And in particular, and this is where the strengths of our methods come in, the number of ancilla qubits, right? So this has 2 to the n amplitudes, but you only need n qubits to do it. So you might not want to use too many gates or too many ancillas, especially if you think more near term. Okay, so quickly, what are approaches that people have proposed? So I think the most straightforward thing to do is to go via an amplitude oracle, where you just okay. So in the first step, you just say you have some oracle that, given an input x, it prepares on the second register that is set to 0 at the beginning. It prepares an f of x. And this x bar is just the grid point we want to look at. And for that, you need to specify in advance to what precision you want to do this, right? Because you know, a certain number of bits. And then, of course, not only that, you actually need to implement this oracle. Now you can just use any like classical circuits if you want, if they are reversible, right? So you need some like reversible arithmetics. And how this is done in practice is often like depending on the exact function, you use some like piecewise polynomial approximation, and then there are some classical methods that allow you to implement polynomials with reversible circuits. And there's a lot of like handcrafting and for every example you want to do this to kind of minimize resources. And also you usually need a lot of ancilla qubits. So actually for simple examples, people often do that anyway, use a QRAM or quantum memory where they just store these values, and it's actually cheaper than going through all of this. Okay, maybe it's more like a small size effect, but this is often done in the literature as well. Okay, so I already said there's some downsides to this.
So with handcrafted, you mean that we are lacking good tools for university algorithms, or what's the?
Well, I just think if you want to minimize the resources, you really have to think about how you want to choose your polynomials, how many pieces you want to put, and then how you exactly want to implement these polynomials. There's a paper.
There's a couple of papers on this, right? They're using matrix product states and so on.
This we'll also see. Matrix product state is a different is different, right? Like from this, right?
Okay.
So actually, yeah. So just to finish the point, like yeah, it's handcrafted, and also you have this discretization at the beginning. And I would actually say that is the main downside of this, that you have to in advance say how many bits of precision you want. You have to discretize to start with, and you know, this can also lead to some like error propagation later if you didn't choose enough bits of precision to start with. And it typically uses a lot of ancillas, as we will see later. Now, Jens already mentioned there are other approaches. There's this Grover-Rudolph approach, adiabatic ways of pairing the state, repeat until success method. They're all kind of like similar. They have the similar caveats as this like standard amplitude arithmetic model. This matrix product state method is different. So you're basically just trying to approximate the state you want to prepare with amplitude then with an MPS. And for certain examples that might work quite well, but I think in general you don't really have like any rigorous guarantees, and it's not clear how it scales and for what states it exactly works. But this might have like a place that is kind of Did I touch the screen now? Or is it?
Now it is working.
I think you kind of like moved your hand to the screen or something.
But I didn't even touch it. Is it like anyway? So I would say all of these fall in the same category, except for the last one, which is might be useful in like orthogonal machines. Good. Anyway, so our approach is different, and it's actually just using a lot of like off-the-shelf stuff that people have developed. It's based on this quantum eigenvalue transformation, which is a special case or a predecessor of this quantum singular value transformation you might have heard of. And this is a framework that allows you to apply functions to the eigenvalues of Hermitian matrices. Right, and this is nice because normally in quantum mechanics you just have like quantum states, and then you can apply unitaries. But here you can really like work with, actually in the general setting you can work with general matrices, and you apply function to these matrices. So anyway, what we want to do is we want to just use that framework for quantum state preparation. Okay. So let me quickly tell you about this framework, just like the main ingredients, not how it works at all. We'll just use it as a black box. So first of all, we have to encode the matrix you want to act on into a quantum state, right? And the way this is done is by these like block encodings. And so basically you have these like three parameters, alpha, m, and epsilon. And so you start with this n times n Hermitian matrix A, and then you embed it into a larger space of n plus n qubits, where m is the number of ancilla qubits. And then what you ask is that if you sandwich with the zero vector on these m qubits, okay, that then you get the matrix A back. Okay, and of course, yeah. So when you embed it in this larger space, you embed it into unitary matrix. So this U is a unitary matrix. It does work. It's a unitary matrix on this n plus m qubit space, and then if you sandwich with 0, you should get back the matrix A. Well, you get it back up to some normalization factor alpha and maybe some approximation epsilon. But okay, set this to 1, set this to 0, and that's kind of the idea. So that's just the definition. And then what QET does is you can now apply any polynomial. Well, in simple case, you use even degree polynomials to this. So this is kind of a quantum circuit that takes this U and then applies the QET circuit. And then the output is a block encoding, but now of a U that if you sandwich with the 0 vector, you get A to the D. Okay, so that's how you get from A to the D. Exactly. Good, and then you can of course ask what is the cost of doing that, like to get from this block encoding of A to the block encoding of A to the D. And this is basically determined by the degree of the polynomial. So D. Okay, so there are some details here, but you see, like you have to apply this U and U dagger each D have many times. So it's basically you have to apply this U D times, and then you have some other simple gates which you also basically need order D many. I think I have a quick example circuit that looks like that. So here X, this is the register of the original matrix A, the n times n matrix. So this is the block encoding. Be more careful. So this is the U of A. So here it's done with m equal to 1. So you have this 1 ancilla qubit A1, and then you actually need another ancilla qubit for the QET circuit. So this is the second ancilla qubit. And then you see, so what you do is you basically switch between applying the unitary from the block encoding and then some C rotations on this ancilla qubit according to some angle. And the angle is, of course, in a one-to-one relation with the polynomial you want to apply, right? So I give you a polynomial, and then you have to compute these angles, and there are D many of them, and then this circuit will take you from the block encoding of A to the block encoding of A2. And yeah, they're actually efficient classical methods to pre-compute these angles. So I'll give you the polynomial. You can compute these angles efficiently. And these methods are more or less efficient in theory and in practice. So it's not a bottleneck of this scheme.
So there's no discretization of the function here.
There is not. There is not, exactly. But it's a polynomial at first, right? So what will happen is actually, if you do exactly that, it's an even degree polynomial.
I'm lost, sorry. Maybe I was hung up on something. I mean, that's working for a degree D polynomial, but you mean this to be part of a spline or something, or some...
well, if you have a general function, you will...
discretized setting of some type. I mean, this is just some part of it.
I will never discretize. But what I will do is I use my general function approximated by a polynomial.
The full thing?
Yes.
Not spline-like, but by...
Well, it depends on your function. So if your function is very smooth, like a Gaussian, you just look at the whole thing on the interval you're interested in, right?
Okay.
Or
because because usually, I mean, I don't know.
You want to discretize, or sorry, I'm not
yes,
sure.
No, I mean, if you, I mean, there's all these approximation theorems for splines of like suitably Lipschitz continuous functions, so on.
Yes.
Well, if you really want to approximate the full function by polynomials, it easily gets totally crazy.
Yes, in general. So there you have to be a bit smart. But okay, so you remember that when I defined the problem, you were on an interval AB, right? So you have to look at interval.
But then that was my question. So basically, you are seeing that as your interval of something else, for example, a spline or something, and then you want a full polynomial interpolation for this interval, and then shut up and don't care for the rest.
Yeah,
it's
exactly
part of a discretization.
It could be. Also, you might, if you have this interval AB and you have a discontinuity, you might actually do it piecewise as well.
Yeah, okay.
Like you can do all these kind of things, but
I'm back on track. Thank you.
Yes, perfect. Yeah, so this exact circuit is for even degree. You can do odd degree as well. And then, yes.
Sorry, the angles theta depend on the degree, but they don't depend on the matrix A.
Yes, they only depend on the polynomial, like also the coefficient of the polynomial.
Okay, the coefficient.
Exactly, yes. And there are some technical conditions which I don't mention here. But like intuitively, you can do something like this for any polynomial. The degree of the polynomial will tell you the cost of the circuit. Good. Yes, so we only need this for like Hermitian A. You can do it for general A. Maybe you've heard of this QSVT. Yeah, just make the connection. Good. So now, how do we use this QET framework to do state preparation? So what we choose to do is to first create a certain block encoding of the matrix A, and we just, you might do other things here. We just choose one that is very simple to do, which is just given by this sine function, right? So you just do this uniform grid, but now you look at the sine function, and the reason is just you can very cheaply implement that by just doing conditional y rotations, right? So you can verify that if you do this thing, you will create a block encoding of the sine, what was the sine amplitudes in there. Good. So that's the first step. And okay, so this is actually, you have one ancilla qubits. The normalization factor is alpha, and the block encoding is 1, and there's no error. So it's a 1-1-0 block encoding if you want. Okay, and then the next step is now to apply the QET to create now a block encoding not of the sine of the axis here, but actually of the function f, right? And to do that, well, we need a polynomial or the function f, so we need like a polynomial approximation of the function f, and then well, since we have this sign sitting there already, we also need to like put an arc sign there, and depending on the interval we are, we also need to shift things a little bit. Okay, so here the question is then, right, what's the degree, the polynomial I need to approximate this function here? Well, this will tell me about the cost of this whole method.
Sorry, where the idea of the arc sign come from?
This is just a very simple or
from the A
cheap
version of A.
Cheap to create a block encoding of that, but you don't necessarily have to put sign. If you have another way of creating a block encoding cheaply, this is, I think.
And just like as in Shor, many of the angles will be tiny and can be neglected, right?
In practice, I guess. Yeah, I haven't thought about that, but sounds reasonable.
Never mind. Sorry, I don't want to debate.
Good, yeah. Anyway, okay, so if you do that, you see you have this kind of non-coherent version of things, right? So you actually want to, now you have a block encoding of this matrix, but what you actually want, you want to create this coherent superposition, this quantum state with having the amplitudes in there. So what you do then is just, you run it on a particular input state, so on the all plus state, okay? So in all of these n qubits, you just put in the plus state, you have these 3 ancilla qubits, and then you run these 2 steps, okay? And then you use amplitude amplification to maximize the probability of outputting this state. So what does it mean? So you measure the ancilla qubits, and if you measure 0, 0, 0, then your main register here will actually be in this state psi f that you wanted to create. And in general, the probability of that happening might only be small with a certain value, but if you run the right number of amplitude amplification, you can actually run a version that is exact, so exact amplitude amplification. So you can really get the probability that this state is on the main register to exactly 1.
And how many iterations do you need for the exact one?
Yes, so that's the question now, right? Like if we want to, so this is the idea, but now if we want to quantify the cost of this, well, you can see it only uses these 3 ancilla qubits. Sometimes we use 4, but now the question is how many gates you need, right? And one factor that goes into that is like how many runs of amplitude amplification you have to run. The other way where you have to quantify things is, you need to find a polynomial approximation here. So you'll have some error here, like how good you approximate the function versus the degree you need of your polynomial. And you basically just have to quantitatively analyze how the error propagates through the algorithm. If you start with a polynomial that is like an epsilon good approximation of this function. Yeah, so let me say a few words for this.
You say the polynomial or exponential? The number of iterations of the amplitude.
Everything's polynomial. Right. Everything's polynomial, yes.
Do you need to do post-selection?
No.
Yes, that's okay, no.
No.
With amplification amplifies what you would do with post-selection. It does it quadratically fast.
Yes. 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 You could also, not do amplification, but post-selection instead. Okay, so I first want to present kind of what are the complexities that come out, and then maybe if we have time, we can talk a little bit like what are the ingredients to get there. But it's basically kind of a boring just analysis, like error analysis. But okay, so what comes into the complexity is this what we call or people call it discretized L2 norm, a filling fraction. Okay, maybe forget about this right-hand side for a moment. I usually also like to draw a picture. I'm not sure.
There's lots of blackboards in this room.
Sorry, Philip?
There's a pen here on the side.
Oh, there's even a pen. Okay. Yeah.
Directly annotate you.
Here?
Yeah. That thing.
That's magnetic.
Even at Blackboard talks using this device.
There's annotate.
It was an Oppenheim game, a wonderful Blackboard talk.
Over there.
What do I have to do?
Well,
Annotate.
Blackboard. Oh,
Yeah.
exactly.
Now you should be able to.
Draw.
You're in from
Even in red. And then there's an eraser. Awesome. Yes. Am I drawing now?
Click on the pen again.
The top left.
Quick draw. And then the top left thing.
Okay. Understood. Okay, yeah. So anyway, so just to why we call this like filling fraction, maybe, I don't know, like you go here from A to B, right? And then, I don't know, you might have some function here on this interval that you're interested in. And then maybe you have this like uniform grid here now. And then maybe here, maybe X, Y. Here you would have some like F max or something. So here in the denominator, you basically just look at the whole area here, where you have the max height of, so this would be like that, okay? The max height, and then you look at the ratio of that, of like this L2 norm of the coefficients in between. Okay, I mean, you can also just take it as a definition. I just wanted to motivate a bit why you might call it a filling fraction. And this also, by the way, in all these other methods, yes, except for the MPS method, comes into the complexity of the algorithm.
Sorry, I have another stupid question. You can just press the don't answer button. But, I mean, why is F max entering? I mean, that's just a rescaling of the whole thing, no? That's just if you shift by constant, that would change F max.
Yeah,
but then also this is the value of the function here, right? Or like if you rescale this both.
Okay, sorry. Yeah, that makes sense. Okay, good.
Good.
No, it's interesting in the same way. Okay, sorry, I missed this.
Yeah, exactly. Yes. So now I have to go back to mouse, I guess. Yeah.
I think you have to click annotate again.
Yeah. Okay. So, So here is the technical version of the main theorem, I guess. So maybe I'll also reveal the start, but okay, let me guide you through it. So you start with a function f. Now you use a polynomial approximation of that function. Call it f tilde. It has some degree d. Okay. And then what the algorithm will achieve is it will prepare a state psi that has the amplitudes of f tilde, right? And this psi is epsilon close in trace distance to the actual psi that had the amplitude of f that you wanted. And then the number, okay, you need 4 ancilla qubits, it's just a constant. The number of gates you need, it scales with the inverse of this filling fraction times n. So n is the number of qubits, right? You have 2 to the n many amplitudes, but this is just n, number of qubits, and then linear in the degree of that polynomial as well. And now, of course, the question is, how does delta and epsilon, how do they relate? So what you need to do is you need to choose delta scaling with epsilon, but then also again with this filling fraction. So one time of the original function, one time of your polynomial approximation. So I'll tell you on the next slide. So maybe this is it's a bit too abstract, like how this scales in practice. There's also some asterisks, right? Because you have this sign, you have to rescale function and stuff like that. But basically, you need this polynomial approximation in L infinity norm, like a worst case kind of approximation. But okay, so here the main scaling is inverse in this filling fraction, and then linear in the degree of your polynomial, and linear in N. Okay. We'll also compare this in a second with the literature and how it's better than what other people are doing. Good. So now if you have a function that is sufficiently smooth, okay, so here's again the technical condition, but in practice, you can always get this, okay? Then, okay, there's a tilde here because there's some polylogarithmic factors hidden. But if you want to prepare this state psi, f tilde, that is epsilon close to what you want, if you want to prepare this, things scale like that. It scales linear in N, logarithmic in 1 over epsilon, and inverse in the filling fraction. And I think this is basically the best up to the polylogarithmic correction terms, I guess, the best you can hope for. And also, you need only this constant number of ancillas. But now maybe I want to erase this. No?
Go and annotate and do clear.
Yeah. See?
Sorry, what's your notion of smooth?
This. So you need, so if you want polynomial approximation in infinity norm, so worst case, up to an error delta. So this is now only talking about the function and the polynomial. Then if you choose a certain degree, this error should decay exponentially. This might sound strong, but if you have if you have discontinuities, you have to do this piecewise. But for example, if you look at a Gaussian function or something nice, this is fulfilled. Yes.
If I have like a direct delta function, then this will not work.
This will not work. But I will look at some examples later. Okay. So for example, you can look at this like triangle function that has discontinuities, and then you just have to do it piecewise. Okay. But you can get something similar then. Yeah, you have to. So basically, in practice, if you want to use these methods, you have to work hard on the classical side of things. You have to be smart on how you choose your polynomial, and there might be a lot of thought going in there. You have to do kind of a lot of classical pre-processing in that sense. You have to compute these QET angles and everything. But once it's set up, the quantum algorithm is very simple. So
Okay, I mean, even more annoying question, but there seems to be no issue of like picking a polynomial basis because you do it kind of directly.
Well, you can choose any basis. It's just the degree that matters.
Okay.
Yes.
So the degree is the limiting thing, and then any dictionary would work in a way.
Yes. I mean, you have to then take this polynomial and translate into these angles from the QET. Right?
Yeah. Okay. I see. Yeah.
Yeah.
Okay.
Fair enough. I guess this is all classical. That's the nice part. But yeah, you have to do something. And yeah. So actually, yeah, Jens, your question, right? Like in practice, you might actually use whatever. A polynomial you want, right? This is about like this rigorous approximation guarantees and rigorous scaling, but actually in practice
okay, sorry.
So you
waited your next thing.
So. Yeah, to prove this, you use this minimax polynomial.
Yeah.
But in practice, you might just approximate this minimax polynomial. This is Remy algorithm, or you do some local Taylor series, or even work with like some L2 approximations on the grid you're looking at. So you can really choose whatever you want, and in practice, like the hidden, at least we're still kind of looking at this like numerically and stuff, but like basically in practice, the polylogarithmic terms and the constants are smaller than 1. Okay, so it scales very nicely. You can use what you want, basically. This is just for analytic calculation. Yeah, it's the next point.
So sorry if I missed something obvious, but like where does the kind of the complexity of f, like if how smooth f is, how does that appear in the overheads?
Well, here it doesn't appear anymore, right? Because I'm just saying f is smooth enough, so we have something like that, and so this tells us what degree polynomial we need, right?
But then the degree doesn't appear in there.
Yes, it doesn't, but we can go back. So this is derived from this one here, right? So here you have the degree, yeah, and then
it's logarithmic, right? It's logarithmic in delta or something.
I know it's just n delta. It's just a degree, or It's linear in
d
the
delta, and then you have an assumption on d delta with respect to delta, right? In the next slide.
This one you mean, or?
No, in the next slide.
Oh, yeah, it's logarithmic in 1 over epsilon. Yes, yes. And this is, okay, so this logarithmic in 1 over epsilon because of this assumption here, right? Yeah, because I say it's that smooth. Yes, yeah, sorry, yeah, thank you. That's what I should have said, yes.
Okay, thanks, yeah. Okay, yeah.
And again, it might look like strong, but this is how it performs and scales in practice. Good, yeah, so this is a table of the literature. The first, yeah, let me again guide you through it. The first one is this QAT that we did, and so this is how many gates you need. Okay, so here we do it in terms of non-Clifford gates, but just total number of gates is the same for this method. And then, okay, so the really strong selling point of our method is that you only need these 4 ancilla qubits. Or if you have some more properties of the function, maybe 3 ancilla qubits as well. And you have these rigorous error bounds. So what you need is you need a polynomial approximation of your function, and the degree goes in here, right? So here I write it just like this d epsilon. This also works with Fourier approximations as a variation of our scheme. But you need something like that here, like this is an assumption on the function. And then if the function is nice enough, this scales very nicely. Otherwise, you have to come up with some tricks. Okay, what are the other methods? Well, you have this like black box amplitude oracle. I think here you also have a polynomial. So it's not exactly the same necessarily. You have the epsilon, the degree of the polynomial is some tilde, which is kind of the maximum degree of your piecewise polynomial approximation of the function. You have an additional parameter here, which is this g of epsilon. This is like how many bits of precision you want, right? Remember, you had to choose that in advance. But anyway, the details are not so important. The point is just that for the second, third, and fourth line here, this oracle-based method, the ancillas, they all scale with the degree of the polynomial that you're using. So this is really the main selling point. So for us, it doesn't. And then even the number of gates we need is very comparable to, or even better than these previous methods. So this is what is nice, I think. And then here, yeah. So we also have this like matrix product state listed here. So Jens, have you seen this like benchmarking practice and stuff? So I can't say much about that. I mean, we don't have this rigorous.
You mean the benchmark for the matrix product state?
Yes. Do people use? I don't know. This is a bit.
I'm not sure I understand the question. I mean, I've thought myself a bit about this, and I know, like, if you give me like 5 minutes, I would be able to produce 3 papers on the subject that take steps into guarantees of what confirmation you need for a given approximation error, given, say, the L infinity approximation.
For a given function.
For a given function, I think also for polynomials, which then also, of course, relates to a circuit because you make it a sequential operation.
I would be interested I don't know, do you think this will do well in practice?
I think it does strangely well in practice. I thought quite a bit about this, and then I got scooped, and then I gave up because there were like then many papers about this.
Yeah, but I haven't seen anything rigorous on this.
No, there is something.
Okay.
No, there's a couple of. I mean, if not, we should revive this actually. But
I'm not like I'm not a super expert on this, but I thought like these methods. Okay, raw root of maybe depending on what exact function you look at, but the matrix product state, I haven't drawn any conclusions from the papers I've seen at least. Yeah, okay, thanks. Yeah. Anyway, this is kind of a literature comparison. Yes, please.
So between your work and the black box amplitude oracle,
yes.
So how does the scaling of G squared compare with the scaling of N?
I don't know. Good question. So, okay, I should say a few things about this. So one is that you might improve on the construction of these amplitude oracles as well, right? It's just kind of what people did, and we kind of copying that. So what we see in practice is that for certain examples, at least, we need slightly more gates than they do, like in practice. But that's just numerical, so I'm not sure.
What gates are we talking about?
Gates, for
T gates, because you have these angles, right? And if you approximate them.
But the angles you compute classically, basically.
Yes, but how many T gates do you need to implement one of those gates?
The RY rotation. Yes, that's actually we have some numerical examples later. Where I mean, you can combine this down in whatever way or what. you need. But I mean, here you can also just read as number of gates.
A good author who took steps into rigorously looking at these MPS is like Juan Garcia Ripoll. He wrote a couple of papers. He was not the first one to do this, but he has an appendix with guarantees. I can look it up.
Yeah, okay. And then because we looked at a couple of papers here, and we also cite a lot of papers. But okay, yeah, if you know,
yeah, I will.
Because I'm not very familiar with the MPS literature.
What is the LaTeX command for this X?
I don't know.
X mark or something.
X. So yeah, that's nice.
But actually, in
smart package.
There is even for some other paper we wanted to put these two on top of each other because the authors claimed that it works. It's not about this, so we had to find a LaTeX comment on merge. I don't know. Andras knows these things.
Yeah, please. Where does the degree of the polynomial come into the black box and to the oracle? Is it that you need a degree?
Yeah, you need to construct the amplitude, the oracle itself, right? And
prepare the oracle, you need the degree, and then...
Yes, I mean the degree, which is the way people usually prepare the oracle is via this piecewise polynomial approximation of the original functions and that sort of thing.
Okay. But it doesn't come into play when you use the oracle to construct a complex.
In their setting or in ours? Sorry.
In their setting.
It doesn't come into play. Well, they just say they query the oracle, okay, but every time they query the oracle, they have to run a certain circuit, and the size of the circuit depends on that.
Sure.
Yeah. Or what's the...
No, the question is the complexity dependence to D is in the construction of the oracle or in the calls to the oracle?
No, the construction of the oracle.
Exactly.
Yes.
Just looking at the Gruber-Rodolph, it seems that G sub E is independent of N. So I don't know if my previous question makes any sense.
Right, but there's no N here, or sorry.
Yeah, there's no N in the black box, but there is an N in the Rudolph. So
here there is an N.
The same G sub E.
That is, well, the G of E is just, like how many bits of precision you want from your function to start this with. Yeah, that's the same.
Okay. Okay.
My understanding was that your question was like, there's no N dependence here, so how do D go?
Yeah, exactly. Yeah.
Okay, good. Yeah, so that's just the comparison. So you can look at functions. The Gaussian is a very important function. So -1, 1, some uniform grid. There's this parameter beta, some assumption of that. This is the complexity we need, right? Actually, this 5/4 one should be able to get rid of, but so it's n times log 1 over epsilon. Okay, so this is really the best you could hope for, I think. And these 3 ancilla qubits. There's this technical condition also. We can do it in a general parameter regime, but then it just looks a bit messier. So that's why I stated this. And so the point is 3 ancilla qubits versus hundreds of ancilla qubits in any other approach, except MPS. There's also this Kaiser window function, which gained some importance in recent algorithms. You can do it for that as well, but maybe it's not so important. Good, so that's on the analytic side. Then we have one numerical example, but we should like research this more numerically. I left AWS and I'm like in Aachen, so I've been very busy, and AWS also, they have their priorities. But in any case, so if you look at this tanh function, people tell me there's some applications of that in algorithms. I don't know. I will admit that it's a bit reverse engineered for us. So this is a function where our method scales nicely. So one should also look at functions where our method maybe you would expect to not scale nicely. In any case, okay, so an example, x between 0 and 1, n equal to 32, right? So that's really 2 to the 32 amplitude. So that's a lot. We have these 3 ancilla qubits. These other methods, like except for MPS, they scale even worse than this, like if you look at adiabatic or something. And you see like the number of gates. Okay, so here we have it in terms of Toffoli gates, and I must admit, I don't remember the exact assumptions or the exact way how we compiled it down to these Toffoli gates from these Pauli rotations, okay? But there are some, let's say, standard methods.
Once we start to implement that, we need to...
Yes, if you really want to implement it down to the exact circuits, there's a lot of work. But that's true for all the techniques,
yes,
right? Like, but this you have to do, But the point here is really like, especially in this like early fault tolerant regime or whatever, you need basically no ancilla qubits, right? It's very different from these other methods. Yeah, and again, like this, to get these numbers, we use like what people claim are state-of-the-art construction of this amplitude oracles. So it might be possible to improve on these numbers. But people tried, and it's not that people didn't work on that. So that's what's out there. Good. Okay. So now, yeah, other methods. Yeah. So I don't know how we are in time or how long this is supposed to take, but this was kind of the main part of the talk. Methods for preparing a quantum state, where the amplitudes are given by some known function. The main selling point is hundreds of ancilla qubits saved with comparable other costs. Now what we should do is, yeah, we should actually look at this more in practice, more numerical estimates for other functions. There are two more theoretically interesting questions maybe that, so there are certain functions for which you don't expect to have a good polynomial approximations, like the square root function. What are you going to do there? You need that. And if you have multivariate functions, you can use that, just amplitude by amplitude, like a variable by variable. But there might be smarter ways of doing it. Like, for example, multivariate Gaussians is an example where anyway, I think that's all I want to say about the main part. Yeah, thank you.
Very cool, thank you. Amazing.
Yeah.
So your theorems were for preparing states with these amplitudes. Or the circuits that you showed were for this A matrix thing where the amplitude.
Yes.
So what are the circuits for preparing these? Like, how do they look like?
Yes, so I have some pictures. Sorry, here. So basically, this is the block encoding of sine, right?
For the matrix A, or for the state.
And this is just the sine block encoding.
The
first step.
It's the A in which you have the sign instead of F.
Yes. So you use that to make the A that you want, which encodes the function F.
The matrix, not the state.
Well, we don't have a matrix, right? All we are given is the function. We have a function f, right?
You had your alpha epsilon m thing, and then you said my matrix A is the sum over f of x.
Yes. And so when you start,
and then there's the state psi that you want to prepare, which is this.
yes. Actually, oh, maybe I should write it.
And is this now for the A matrix or for preparing the psi state?
Even before that, the first step. So the first thing you create is just, well, up to the grid and whatever this sine of x thing, right?
Okay, yeah, oh, sure. Then.
Something like that. So this is step one. This is this circuit. This is step two. This is this circuit. And this is step three. This is that circuit.
So that thing turns your matrix into the state. It's the amplitude. Oh, is that the amplitude amplification?
Yes, I mean you run it on the plus state, right? And then you do amplitude amplification.
Okay.
And this is this part here, right? You run it on this all plus state. But okay, let's go straight quickly, maybe. No, I mean, like this is, sorry, yeah, this is the sine thing, right? And then this whole circuit actually goes in this. Oh, use sine here. This is exactly this circuit every time you put it in here. So then this is the QSVT or QET circuit, and then this whole thing is UF tilde here. So this whole box again is a box here,
okay.
And then this is the overall circuit you run, and this includes these are the rounds of amplitude amplification. These are your ancilla qubits. So since we use this exact amplitude amplification, you don't even have to measure your ancillas unless you expect some errors. But then on the main end register here, this is where your state will register.
But it's not those topology gates that you counted, right?
Just all of them.
Yeah, but like, how do you convert single qubit rotations into topology gates?
Well, there are ways of doing that, right? Like that people use to do estimates. Okay, look, I'm not an expert, but I mean, this whole Google Quantum AI group, they do all these research estimates for like quantum chemistry, whatever. They use some methods to compile this stuff. Yeah. Like this is in the literature.
The simplest level.
But I'm not saying this is like. But okay,
Yeah,
so look,
as a wonder, how do you get these numbers?
if you can improve on that, all the better, right? Like these numbers are conservative in the sense that if you use some off the shelf stuff, you get these counts and these numbers. So if you do something,
There's a worst case statement.
yes.
So what you presented is like ways of preparing states and code functions, right?
Yes.
But preparation is only part of the trouble, right? I mean, you want to do something with it.
Sure.
I mean, there's this. I mean, the framework I mentioned by Garcia Ripoll on like quantum-inspired classical methods of manipulating functions. So the whole point is that you can do something with functions, run algorithms on top of them. So how easy would it be to kind of manipulate the states in a kind of satellite type way of looking at differential equations or something, or running quantum algorithms on top of the encoded functions? Because, well, it seems to be only part of the trouble. So is it a convenient way of manipulating things, of computing properties thereof, derivatives? I don't know whatever you want.
You haven't thought about that at all, right? Like, okay, so
here you stopped at preparation. I mean, that was
exactly. So if you here just on this n qubit, you get the state, it lives there, so that's that, right? But then you want to do stuff with it. Yeah, I see.
Because I mean, I don't know, if you spend quite some time on a similar problem, namely using, well, actually, we wrote a paper on this function approximation in a slightly different way when we looked at learning dynamical laws from data, like in this kind of Hamiltonian learning mindset, but really classically, where you take like snapshots of data in time, and then try to find like right-hand side of differential equations that best capture the actual dynamics.
Okay.
And I mean, like, well, you're going to define a function dictionary and pick whatever you want. And then a common way of doing this is just the best square fit given the data, regularized in some suitable way, say in an L1 norm way that represents inspired. And that's completely obvious, but that is often used and it creates lots of citations under SIMD as this kind of sparse identification of dynamical data. And if you want to be scalable, then you have to find some way of creating a dictionary that is scalable to have a good hypothesis on the problem. And one hypothesis that works well is like picking a local function dictionary and then expanding this function dictionary and uplifting this to the full space by a tensor network construction. Like by matrix construction. So that the bond, the physical bond is not labeling like elements of a complex vector space, but actually labels of a function space.
I see.
Yeah?
Okay.
And that's actually quite nice because then you can really recover. We already covered papers about this. You can nicely recover dynamic laws from data. You stay at some nonlinear whatever problem, and then you can really see the right-hand side from this by using like tensor network recovery methods.
Okay.
Why am I saying this? Because then similar questions arise, like how well can you approximate a function given a dictionary, but then also questions arise on how to manipulate them. And once you have good function, then like derivatives and so on are super easy because, well.
Yes. So the only thing I can say is like this is all inspired by this QET stuff, right? So where you kind of process matrices, this is kind of how you translate it, like to states. So if you have anything in this original framework, maybe you can translate it to here as well, right? So for example, if you can take like, okay, I don't know what happens for states, but right, they do like sum and multiplications of blocking codings, stuff like that, but what things you would want derivatives? I see.
I think derivatives. I mean, you assume a very strong oracle to F here, which allows you, for instance, to create the binary oracle to F, right?
Yes.
There you can use like Stephen Jordan's algorithm, which gives you derivatives very quickly. You know, it uses like this. I think Gillian, Andash.
Yeah, Andash. I don't know.
That thing is actually quite powerful, then, and with this very strong oracle to F, you can actually get derivatives very efficiently.
Okay.
So I'm not sure if derivatives will be the go-to application. But
Yes. So for us, yeah, we it's really a black box thing. Like, okay, you want to prepare a Gaussian? How do you do it? Like, here's a circuit, and that's when we stop thinking about it.
I mean, that said, I mean, even your machinery might even be useful in our context, in this learning context. We should even talk about this.
Yeah, is this something you guys already did, right? Or like, or
yeah, no,
work in progress?
Did and do. I mean,
okay,
yeah, we wrote.
Yeah, no, I'm happy
two papers about this.
Okay,
there's 3 papers about this already. So that's something.
Yes. Yeah, it might be.
One is like very cowboy-like. The other one is a bit more mathematical, and the one that looks a bit more at the numerical procedure.
Yeah. So actually, yeah, no. This would be great because the reason I like to talk about this sometimes is that because I think people should try to use this black box or just this ingredient in whatever algorithms they're running and to see like how it performs in practice and how it can be extended in some way. Good, very good. Thanks a lot.
Mario, I have a question.
We have video here.
Yeah, can you hear me?
That's Jakob speaking out of the machine. Very good.
We can hear, we cannot see, but hear.
Okay, great.
Here.
Thanks for a nice talk.
Now I can see. Yes, thank you.
Okay, great. I kind of realized that I've been confused for years about another result that's related to this. So I'm going to kind of ask you about it. Maybe you have some thoughts on this. So there's this paper by Aronov and Tashma from I don't know, way back, maybe 2005 or something like this. And they were in it, they kind of defined this problem called quantum circuit sampling. I don't know if you're familiar with this, but it's kind of basically the task is to prepare a quantum state that has amplitudes that are like the square roots of probability distribution, where the probability distribution is defined by a classical circuit. So you choose a random bit string and you input into a classical circuit, and you do like these AND OR gates, and then at the end you get some bit string out, and the distribution of this bit string is what you're encoding, right?
And then you want to put this in a quantum state as amplitude.
Yeah, you put it in a quantum state with the square root probability. Yeah, that's right. And then they say that one of their results is that basically the complexity class statistical zero knowledge reduces to solving this problem or doing this preparation. So, and SZK should be a really hard complexity class, so you shouldn't be able to do this. And this kind of, so for years I just thought that means that preparing these states is really hard, but maybe the hard thing is actually not preparing the states, but somehow getting a classical function to describe that probability distribution. I mean,
but what circuits are we looking at? Like general circuits?
Yeah, any classical circuit.
I see.
Yeah,
I
it's
see.
kind of a weird setting, right? Like, I mean, it seems like it shouldn't be, the degrees of the polynomials and stuff shouldn't be the obstacle there.
Well, you mentioned square root also, right? I don't know, like we had square root in the Outlook as so from our specific method, but I see. Yes. But then if you run the circuit once, right, you just get one outcome. So then how do you get these probabilities into the... So actually, I don't know the work and I haven't thought about it, but it's an interesting question because you're saying they show, the overall thing is hard. I see.
Yeah, but I guess I mean there's like 2 steps that are hard. So I guess one is to actually write some function that's close enough to the square root of the probability distribution, because you don't know what the probability distribution is. You can kind of estimate to polyprecision any particular probability, but to write a function for the whole thing, maybe it's just, maybe that's the hard part.
It might be, yes.
It seems like your work suggests that.
I think that would be my first reaction, yes. Like if you would know this distribution, then you could, like all the entries, then you could, it should be relatively simple to prepare the state. But okay, I'm not sure. Yeah.
Okay, cool. Thanks.
Thank you.
Nice.
Good. Should we?
Any other question?
Yeah.
Okay, so let's thank Mario again.